We're now going to have three different examples where we have piecewise functions and we want to find values a and b that actually allow us to connect our piecewise functions so that they are continuous. So our first piecewise function is f of x is equal to x squared minus 1 over x minus 1 when x cannot equal 1 because we have a domain error, and then a when x is equal to 1. So we should by now be able to identify that we're going to have a removable discontinuity in our first function, because if we factor our numerator, we're able to cancel out an x minus 1 in both the numerator and denominator. So that leads us to the question, where does that hole occur? We know that the hole occurs when x equals 1, but what is the y value when x equals 1? So what we need to do is we need to plug that x value of 1 into our new simplified function to find the y value of the hole. So let's start by factoring, simplifying, and then we can plug in. So our numerator factors difference of squares, x plus 1 times x minus 1 over x minus 1. As we said, we have a removable discontinuity when x is 1. It means we simply just have a hole at that particular location. The function y equals x plus 1 is the same exact equation. We just need to take into account that the hole occurs when x is 1. So what is the y value when x is 1? Let's plug it into our new simplified expression and find out. So we have y equals 1 plus 1, therefore y is equal to 2. We should know that f of x is the same thing as saying y. So we want our y to equal 2, therefore a is equal to 2. If we graph our first part of the piecewise function with the hole at the ordered pair 1, 2, our a value of 2 will allow us to plug that hole, because when x is 1, our a is then 2. Let's take a look at another example. For our next piecewise function that we want to make continuous, we have the function f of x is equal to the square root of x when x is greater than or equal to 4, and then we want to find a so that ax squared when x is less than 4 connects it and makes it continuous. If we plug in 4 for x into our first function, we will then find that our y value is equal to 2. So that means our first function starts at the ordered pair 4, 2. Therefore, our second function, the ax squared, must end at that same point, that same ordered pair 4, 2, so that they connect. 4 represents the x value, and 2 represents the y value. So let's plug in x and y, and we can find a, because there's only one unknown variable. So f of x is the same thing as y, so we can now plug in 2 for y is equal to ax squared, but our x is 4, so a times 4 squared. 4 squared is 16, so 2 equals a times 16. And then if I divide both sides by 16, a is equal to 2/16, which is equal to 1/8. So the function that would piece together with the square root of x in order to make our function continuous would be f of x equals 1/8 x squared when x is less than 4. So our a value is equal to 1/8. You can take these functions, plug them into your calculator, and because of all of the algebra that we've done, they will connect and be continuous. We have one final example, and then we'll talk about the intermediate value theorem. Our last example of putting piecewise functions together and making them continuous is probably the most complicated, but if we break it down, we can clearly find where we need our function to start and end. Here we have the function f of x is equal to 3 when x is less than or equal to negative 2, ax plus b when x is greater than negative 2 and less than 4, and f of x is equal to -6 when x is greater than or equal to 4. Take a second and just sketch what the first and last functions look like. Here's a rough sketch of what the first and last pieces of this piecewise function look like. Two horizontal lines. So we need to find a linear function, ax plus b, similar to y equals mx plus b, that will connect these 2 points. So you should see from our quick sketch, sorry for the squeaking, the first function up here ends at the ordered pair -2, 3, that point. Our last function starts at the ordered pair 4, -6. So, in order to find the linear equation that connects those 2 points, we first need to calculate the slope between those 2 points. That will be our a, because it falls in the same part as our m in our slope-intercept form. And then we can plug an ordered pair, x and y, either one, and our m into our equation to find b. So let's get rid of this graph and give us some room for the algebra. So first thing we're going to do, in order to find slope between 2 ordered pairs, we need to use our formula y2 minus y1 over x2 minus x1. I'm going to call -2, 3 my first ordered pair. So I have x1 is -2, y1 is 3, 4 would be my x2, and -6 would be my y2. So y2 minus y1, I'm going to have -6 minus 3 over x2 minus x1 is going to be 4 minus -2. -6 minus 3 gives me -9. 4 minus -2 means 4 plus 2, which is 6. So that means my slope is going to be -3/2. There's my m, or my a, whatever you'd like to call it. So we're going to go to our y equals mx plus b form. We're going to plug in -3/2 for m, and we can select either ordered pair for our x and y. I'll choose the second one, just for fun. So we're going to plug in -6 for y. Our m is -3/2. X is 4 plus b. By plugging in one of my ordered pairs, I then only have one unknown variable, which is b. So I'm able to solve for that. If I multiply my -3/2 times 4, I get -6. So I have -6 equals -6 plus b. Then to solve for b, when I add 6 to both sides, my b is equal to 0. My b is my y-intercept, so my y-intercept is 0. This particular function crosses the y-axis at 0. So I now have my b value, I have my m or my a value, so the linear equation that connects my first 2 functions, actually my first and my last function, is going to be f of x is equal to -3/2 x. You can put the plus 0, but it's irrelevant. So that is the function that will actually make our piecewise function continuous and connect my first and last functions. Stick around for another minute. We'll talk about the intermediate value theorem very quickly, and then we'll be done.